Hi everyone. This series of videos will take you through Lesson 8G in the packet, which spans pages 10 and 11. I should make a quick disclaimer that in order to understand this lesson fully, you should have completed the Desmos activity in the learning plan on Tuesday the 28th and understood the basic shape of an exponential graph. The exponential graphs that we'll be exploring today, which you can see in question number 2 as a preview, are going to be the shapes that you were doing that marble slide activity with. And hopefully at the time you did that Desmos, you made some observations about what makes the shape look a little bit different from equation to equation, and a few general features of the shape. So before I start question number 1, I do want to take a couple of seconds to just make a couple of quick notes about some of the observations that you hopefully made while you were doing the Desmos, so that you can go into this lesson with the necessary foundations. I'm going to do this in my notes part of my packet, but if you didn't print the packet, or if you just prefer to take your notes somewhere else, that's fine. Here are some general things you should know. First of all, the family of exponential equations very much resembles the family of geometric sequence equations. It's almost the exact same thing, where instead of n and t of n, we're using x and y. That's one major difference. And now we're calling the initial value and the multiplier by slightly different variables. They probably aren't as intuitive. Initial value would be the value a, and the b is the multiplier, but hopefully you've made that connection no matter what the letters are, that the initial value is the number that is not attached to the power of x, the multiplier is the number attached to the power of x, and those are just like sequence numbers. The initial value is the starting value or the zero term in the pattern, and the multiplier is what makes the pattern continue to the next term and the next term and so on. Now the general shape of an exponential graph, as you saw in the Desmos, totally depends on the value of the multiplier. When you actually have a multiplier, there essentially are two possibilities that you're going to encounter. The multiplier is either going to be bigger than 1 or smaller than 1. Now, it is possible that the multiplier is equal to 1, and we'll talk about that, but let's consider both possibilities for a second. Either the multiplier, and sometimes your b's end up looking like 6s, so do the best you can. That made it just about the same. But either way, make sure that you're kind of noticing here that the value of the multiplier itself is going to dictate the shape of the graph. When you had a multiplier bigger than 1, the shape generally looked like this. And there's my x and y axis, just so you have reference. The shape generally looked like it was flat on the left and then gradually curved up as you go towards the right. Now the flattening on the left is due to an effect you've seen before in a couple of different graphs that we've explored. That flattening effect, is caused by what we call an asymptote. And in this case, the asymptote is the x-axis, because if you actually zoom in, and hopefully you did this on Desmos, the graph gets really, really close to, but never really touches the x-axis. So that means the x-axis is acting as an asymptote. You can say that its equation is y equals 0. That's technically the equation of the x-axis, but it's more just knowing that it's there. Now, the general curve is definitely important to notice, that it's always flat on one side and curves up on the other. But remember how I said a couple of minutes ago that the actual shape depends on the multiplier? Here's what happens if your multiplier is less than 1. If your multiplier is less than 1, then the graph actually starts out up high and flattens as it goes towards the right. So almost like a mirror image, if you will. And we call this a decreasing curve, because if you go from left to right, it starts out really big and then gets smaller and smaller and smaller and smaller. And when I say it, the y coordinates are getting smaller and smaller and smaller and smaller. So we say that this has a decreasing shape, contrasted with the first one I drew, which has what we call an increasing shape. It starts out with very small y coordinates, and then the y coordinates get bigger and bigger and bigger and bigger as you go to the right. The graph in both cases does have an asymptote. The asymptote is still the same x-axis, or y equals 0, but that's not the important part here. The important part is really just noticing the difference. In fact, the name of the type of curve, increasing exponential or decreasing exponential, that I just mentioned, really does harken back to the actual value of the multiplier that we just discussed. Remember how we said the two different possibilities are that the multiplier is either bigger than 1 or less than 1? Think about it logically. If you have a pattern where the multiplying factor is bigger than 1, so you're multiplying by 2, multiplying by 10, multiplying by 100, whatever, then obviously your pattern is going to get bigger and bigger and bigger and bigger. Because multiplying by 2, for example, like let's say you have 5. 5 times 2 is 10, times 2 is 20, times 2 is 40, times 2 is 80, times 2 is 160. The values are getting bigger and bigger, and those values really are just your y-coordinates. So that's why we call this shape the increasing exponential, because both the multiplier is increasing and the shape of the graph is increasing. The graph starts out flat and gets bigger and bigger and bigger and bigger as you go to the right. By contrast, the other situation, where the multiplier is less than 1, would be called a decreasing exponential. That one's a little bit harder for people to think about, so an example might help. Think about what would happen if you have a multiplier less than, like a half. Multiplying by a half is the same as dividing by 2. So picture a pattern, like say I started with 100. Well, 100 divided by 2, because remember, if the multiplier is less than 1, it's like dividing or multiplying by a fraction. So let's say divide by 2 would be 50, divide by 2 is 25, divide by 2 is 12.5, divide by 2 is 6.25. And because you're getting smaller and smaller and smaller and smaller every time you multiply by that half, or every time you divide by 2, that's why the curve eventually starts to do this. Now, interestingly, the reason for the asymptote is because if you think about dividing, and I think dividing is a particularly powerful way of seeing this, if you think about dividing with the example that I just mentioned, like take 100, divide that by 2, and then divide that by 2, and then keep dividing and dividing and dividing and dividing and dividing. Do you notice how the numbers just get really, really, really small, but they're not actually 0? Like, notice I'm down into scientific notation at this point. This is like if you move the decimal 4 places to the left. So I'd have 0.00007629. That's really small. But I'm getting smaller and smaller, and it's not actually ever touching 0. I've got 0.00000 craziness, but it's not actually touching 0. And that's why an asymptote happens. It happens because as you keep going, the numbers get smaller and smaller and smaller. They're really close to 0, but they're not actually touching 0. And that is, by definition, what an asymptote is. It's that line that you can get really close to, but never actually touch. So hopefully, as you explored the Desmos, you did pick up on some of these key observations, namely the shape of the curve itself, the fact that it's flat on one side and kind of spikes up on the other, and the fact that it has an asymptote. Those are really important facts that you need to know about the shape of the graph. It's also important to know why the shape of the graph is what it is, and remember that the shape of the graph, the increasing or decreasing shape, is caused by the value of the multiplier. If the multiplier is bigger than 1, then you have an increasing shape. It's flat on the left and spikes up. If you have a decreasing graph, it's flat on the right. So from left to right, it starts up high and then flattens down. And those two things are basically the main ideas that you need to know about these graphs. The last main idea that hopefully you put together was that in the Desmos activity, the initial value wasn't really called the initial value. You basically were referring to it as a y-intercept. So I'll make that little note here just so we know. The phrase initial value was something that with sequences we used a lot. But when we talk about exponential graphs, it's actually a little bit more useful to just refer to it as the y-intercept, because we're just going to be focusing on graphs. We're not going to be focusing so much on like context where we're talking about a situation where you have to know the initial value because that's what's going on in real life. Most of the time when you use the initial value for graphing purposes, you're just using it as a y-intercept. So this point here, if I had just made this up, would be whatever the y coordinate of that number is, or the initial value. So if, for instance, I wrote a mock equation, let's say this was 5 times 2 to the power of x, this a, or this initial value, would just mean that the y-intercept is at 0, 5. The same thing is true of decreasing exponentials. In fact, the y-intercept plays the same role in both types. So if this, for example, was for the equation y equals, let's say, 2 times 1/8 to the power of x. I just made something up. But this is your a, which means that the point on the y-axis is at 0, 2. So the value of the initial value is just the y-coordinate of your y-intercept, or you can think of it whichever way you want, starting point, whatever. The shape, again, is dictated by the value of the multiplier. If the multiplier is bigger than 1, curves up. Multiplier is less than 1, curves down. And finally, just to kind of answer one more bit of unfinished business, if you thought about what would happen if the multiplier was exactly 1, hopefully you kind of picked up on the idea that if the multiplier was exactly 1, let's say we had 5 times 1 to the power of x, think logically about what that would look like just as a series of values. If x is 0, then the y-coordinate would be 5. If x is 1, then we'd have 1 to the power of 1 times 5. If x is 2, 1 to the power of 2 times 5. X is 3, 1 to the power of 3 times 5. And you just end up with 5, 5, 5, 5, 5, which, if you graphed it, would just be a series of points in a line. 0, 5, 1, 5, 2, 5, 3, 5, which is a really boring graph. In fact, it's not curved at all. It's just a straight line with a bunch of y-coordinates at 5. So that's why we don't really talk about what would happen if b is equal to 1. It's because it's kind of nondescript. If b is equal to 1, you just have a horizontal line at y equals whatever the initial value is, and that's not really a common situation you should worry about. So hopefully that gives you some notes, some foundations, and then once you feel like you have the basics down, you can proceed into the rest of page 8.